All right, so we've talked about the mechanism of catalytic hydrogenation of alkenes. We've seen that it also works for alkynes. But what we haven't talked about yet is how to selectively reduce an alkyne to an alkene. So we're stopping at the alkene, not going all the way to the alkane. So we can do this to either form the cis alkene or the trans alkene. So first of all, what does that look like? Well, the cis alkene has those hydrogens on the same side versus the trans alkene is going to add the hydrogens on different sides of the molecule. So one thing to just point out right at the start is, what is a more stable molecule? A cis alkene or a trans alkene? So think about that for a second, pause the video, and then restart it so you can at least give this a little bit of thought. And now that you've done that, it turns out that the cis alkene is less stable. So why was that? Again, that was because the bigger groups, the CH3 and the CH3, are on the same side, so they're sterically crashing together. They're too close. It's not very favorable. But it turns out that we can make either one depending on the method. But we'll just note from the start that this is less stable. This is the more stable alkene. And that's kind of important for why this method is going to make that more stable alkene. So why does the cis alkene, how are we able to make it cis since it's the less stable one? Well, the mechanism of the reaction is going to determine if the two hydrogens add to the same side or if they add to different sides. And if you think back to the mechanism of a catalytic hydrogenation, so if we have H2 and palladium on carbon, if you remember correctly, the palladium kind of sits like this with the hydrogens on the surface. And those hydrogens get added very quickly to the pi bond in a concerted way. So we'll just write the H's add concerted. And because of that, it turns out they add to the same side. Same side. So you can imagine if this is the pi bond right here, and we add both of them at the same side, the pi bond is going to essentially the molecule has to change itself to put the rest of it on the opposite side. If these two hydrogens are adding to the same side, the rest of the molecule has to kink away from those hydrogens. So the mechanism of a catalytic hydrogenation makes it a reality that they have to add to the same side and make this cis alkene. The next question you probably have, though, is, we already saw this. We already saw that if we add hydrogen and palladium on carbon to an alkyne, that it's going to make not the alkene, but it's going to reduce all the way to the alkane. Because if we add hydrogen once, there's no reason why we can't add hydrogen again. And that's true. So we have to use a specific catalyst for this reaction. It's still palladium-based, it turns out. It just has some other additives, and it's actually called, it's most frequently referred to by the name of the person that discovered it. It's called Lindelar's catalyst. Essentially, Lindelar's catalyst, again, I said it's palladium-based, so it's still the same type of metal catalyst, but it isn't as active. So just the palladium on carbon by itself is so active that it's going to add hydrogen there, then it's going to add it here. There's no way to stop it. It just kind of runs away without you being able to slow it down. The Lindelar's catalyst is a slower catalyst. It's less active, so it allows you to add a single equivalent of the hydrogens all to that same face. But because it's still palladium-based, it still adds them in a concerted fashion to that same side. Okay, so that's how we make a cis alkene. We use hydrogen with Lindelar's catalyst, so it's another catalytic hydrogenation. What about a transalkene? So transalkenes, we're going to have to use some other type of reagent because if we use any type of metal catalyst, it's going to work by the same mechanism that we've already described. So we have to do it a little bit differently. So it turns out that we add sodium metal, and I put a 0 by that sodium. That means that sodium is elemental. So as far as elemental sodium, what does that look like? Well, elemental sodium has 1 electron. So here I just put sodium with the 1 electron. And elemental sodium doesn't want to be, it doesn't want that electron, right? All atoms want to have a full octet. And sodium, if it just gets rid of that electron, if it gives it away, it will gain itself an octet. So essentially, when we have sodium in a reaction, it's going to go from sodium 0 to sodium plus 1. And in doing that, it shoots off an electron, which we're just going to show as E plus, or sorry, E minus, because electrons are negatively charged. So when we have sodium in a reaction, that means that we have a lot of electrons floating around in that reaction, ready to react. And it turns out that they can react with the pi bonds of an alkene. So that electron is going to move up there. We're using the single-headed arrow, remember, the barbed arrow instead of the double-sided arrow because each side indicates 1 electron, and we're only using 1 electron here. Then the pi bond is going to break. One of them is going to combine with that electron, so they kind of meet in the middle, and then the other electron is going to sit on the other side of that alkyne. So at this point, we no longer have our alkyne because one of the electrons joined up with this electron here and is now negatively charged on that carbon, and the other one is that unpaired electron right there. Okay, so we have to, so now we've used an electron up from our sodium. We have to also have some source of hydrogen. It turns out that sodium metal we can't run a reaction with sodium metal. It's a metal, so there's no way to really get just that in contact with it. We need some type of solvent. So the solvent we've seen a lot recently is ammonium, NH3. And if we remember our pKa as well, we would remember that ammonia has a pKa of 38. So what has to happen next is an acid-base reaction. Anytime we have electrons that are nucleophilic, that are basic, if there's an acid around, they're going to be attracted to the partial positive on that hydrogen, and they're going to protonate from that acid. So if we look at the equilibrium between this, we now have NH2 minus, and we have this hydrogen here, the pKa of a hydrogen off of an alkene is another one that you should know. That's 44. So the equilibrium is moving away from the stronger acid here. This should work no problem. Okay, so one thing we haven't talked about is I broke that alkyne and I immediately drew the transalkene. Why did we do that? Well, if an alkene is going to break in this stepwise manner where it just breaks and it puts electrons there, and then it's going to add a proton and there's a lot of steps, it's going to break into the conformation that makes it most stable. And we already said transalkenes are more stable than cisalkenes are, so that's why we get the transalkene here. How do we get to the final product? Just these same exact steps again. We have more electrons around because we have more sodium around, so more electrons will combine with this unpaired electron there. That would form this anion here. And that anion, there's still going to be lots of our solvent around, so it's going to take part in another acid-base reaction to produce the transalkene. So if we want the cisalkene, we use a catalytic hydrogenation with Lindlar's catalyst. If we want a transalkene, we use sodium and ammonia, and this has a name. Sodium is a metal, so remember, elements in the first group are called, I guess just everything to the left is really a metal. So this is actually called a dissolving metal reduction. So sodium metal is dissolved into the ammonia solvent, and electrons are generated from that process, and those electrons are what are used to reduce the alkyne to the alkene. So that is how we make a transalkene from an alkyne. Let me see if I didn't put anything in here. Nope. That is pretty much everything. So thanks for watching the video, and we'll talk soon.